So again, thank you, DK, for the interesting presentation. In the next session, I'm going to introduce myself again. I'm going to speak a little bit about the things that happen in the development side, both on commercial and non-commercial system architecture. And I think after the next 15 minutes or so, 20 minutes, we're going to have the first break. So if you need coffee urgently, it's coming in 15 minutes. So as part of what we do within the organization, we also work with different end users and companies and so forth, understanding where things are going and also provide some of our insight. And HPC is a place that, definitely trying to get higher, better and better performance, and there is always the greater need to improve system capabilities. But one thing is probably clear. If you want to get greater performance and if you actually want to make the big jumps in capabilities, doing more of the same things will not actually cut it. So it can help you to increase in some sort, but unless you do something really dramatic, typically you cannot get big performance improvements and abilities. And there is multiple examples. And one example is breaking the latency wall, or the application latency wall. So if we take a little bit step to the past and look on what we have done so far in trying to reduce the latency numbers. Around 10 years ago, if you look on communication frameworks latency, and DK can definitely give from his perspective, hopefully confirm. If you look on the interesting latencies of communication frameworks, if those are reduction protocols or aggregation protocols, latencies of those elements were in the range of hundreds of microseconds. At the same time, the network latency was in the range of tens of microseconds. So it was kind of a big part, or not a negligible part, of the communication framework latency. And then most of the focus on reducing the latency was actually put on the network side. Meaning, if we get the network latency to become almost nothing, then we actually reduce the communication framework latency, which is a good thing. So if we do a fast forward to today, if you're going to measure communication frameworks or aggregation protocols, for example, reduction protocols, if you measure MPI latencies of those, for example, collective operations, you can easily be in the 20, 30, 40 microseconds of operations in a decent system. On the other side, if you look on the network latency, that's actually something that today we measure in nanoseconds. So network devices today are measured in hundreds of nanoseconds and even less. So if we continue what we did so far, we actually cannot gain any more from that. Because if you take the network latency and make it 0, you reduce another 1 microsecond or 2 microseconds from a 40 microsecond or 30 microsecond operation, which doesn't give you anything. So the question is, how do we make the another 10x jump, assuming that from a network perspective, you almost hit the laws of physics, and you cannot actually go to almost to completely 0, but you do want to gain another 10x performance improvement in the latency part, and you continue to reducing latencies of those operations. To do that, you need to do something else. You cannot continue with what you did so far. And if we take example on the coral systems, and one of the larger coral system, which is one in Oak Ridge, the Summit system is now being built actually. And look on the requirement that were put on Summit, you can see the different elements from performance perspective, which is to gain 5 to 10x higher application performance versus the Cray system that exists in Oak Ridge. The architecture of the system was changed. So instead of having lots of nodes, almost 20,000 nodes, it's kind of becoming fat nodes again, kind of going back history. So putting more GPUs, fatter network pipes on each nodes, but with around 5,000 nodes on a dual rail network to be able to get that 10x performance improvement. We can go through the other elements, but I think this is kind of connect me to the previous slide. So running barrier latencies of almost 100 microseconds. On Titan, the wish was to go to 4 microseconds. So that's kind of to make almost two orders of magnitude of reduction. And you cannot do something like that, again, doing the same of what we did so far. You need to do something else. And it applies to other areas. As DK started to work more and more in machine learning or deep learning and AI, the reason is because AI and HPC is very, very similar in the needs. But AI is bringing other elements because now it's moving us to a different kind of protocols or different kind of things that you need to do in a system in order to run those frameworks. So it's moving from a compute-centric to actually data-centric because now you need to analyze growing amount of data and you need to find insights in real time and so forth. So the way that we traditionally analyze data, it's not something that is feasible anymore. And the same approach, by the way, goes to outside of the HPC, outside of the data center. And one very simple example is looking on IoT. Because in IoT, the first idea was that we'll put sensors everywhere, and then we'll move all the data to the data center, and we're going to analyze it there. But it's not feasible. Because you cannot move huge amount of data over and over to the data center and only analyze it there. You actually need to do something else. Instead of moving data to the compute, which is what you have on the left side, you actually need to start moving compute to the data. So it's kind of changing the way that we act or build systems or created architecture so far. Now, the most expensive thing today, it's actually moving data. And this is an example for FedEx, but there is growing amount of data. You need to do more complex things. And moving greater and greater amount of data, it's the most expensive thing that you have today on the system. And this is something that you need to try and figure out how to deal with in a different way. So you need to break the trade-off as well because the native approach was I have more data volume and I need to do faster data analysis, which means traditionally I need to throw more cores to the problem. But when I throw more cores, I actually create more communications that need to run between the cores, which actually increase the latency and make it even worse. So this is kind of something that needs to be broken. And the way to do it is what people start to work on in the last couple of years, which is something that some people call it co-design, some people call it in a different way. But let's bring us through a third major transition in a data center if you compare it to the last years. So I named two other big transitions that happened. The first one was moving from SMP to clusters because it was breaking the cost of the system and make it much easier to scale and to grow the system and so forth. That was one big transition that carried us all the way to today. The second big transition was from moving from a single core to many core. Cannot get more performance from CPU on the frequency, so let's have more of those. And now we're going through a big third transition, which is the co-design transition or the data-centric transition. You can find different words for that. So what does it mean from a data center perspective? It means that if in the past, those were the elements that we actually run compute. Everything else was used maybe to store data or move data, but this is where we run compute. And as we move to a data-centric approach, actually going to start running compute on the network as well. So now the network is not just to move the data, the network is also an element that can actually run compute. And compute on the data is a data move. So if, for example, I can do reduction elements on the data as a data move, which is a very native idea or very simple idea to start with, then I can really cut latencies on one side, and on the other side, I can really reduce data that needs to be moved, which is the most expensive thing. So this is the first step. Second step is actually move compute also to the storage. So you want to be able to work on the data or analyze data wherever the data is, not just on the compute side. So you analyze the data as it moves, you analyze the data as it store, and this is a project that Google is working on, and you also analyze data on the CPU. So it's not more, I'm going to throw more cores if I need to analyze more things. It's, I'm going to design my system in the right way that I can get compute from different elements. Yes? Right. Right. And this is within the data center. Once you go outside, yes, you put it there. Because if you go back to IoT, in IoT perspective, now you're going to actually have a data center in your house. And actually, on the edges. On the? Right, right. You're going to do also compute on the edges. There is some places that already today that you actually cannot store the data and analyze it after. And another example is the SKA project, which is the building the square kilometer array, which includes multiple countries and organizations and so forth. They build huge amount of telescopes, and then they collect information, and then they need to move it in order to find some insights or figure out the origin of the world or the universe. In the way that they work, once the data goes from the satellite, they actually analyze that as they move it. And they use FPGAs, and they use smart network elements and so forth. And they get trying to find the elements that they actually want to keep for their analyzing. The rest of the data they need to drop. Because first, there is too much data to store. The second thing is, if I were able to store all of the data, why would I come later on and analyze data if I have a new data that just came in? Doesn't make sense. So as the data gets in and you collect it, and that's kind of related to the question here, you need to figure out what's the main elements that you want to keep, and then all the rest you're going to drop. If you look on financial transactions, and take for example, PayPal. When you do a financial transaction, PayPal wants to give you yes and no, and then after they give you yes and no, they don't care about it anymore, basically. So if they can give you the answer and run their algorithms as you put that information of what you want to do, then it's much easier for them. They don't want to bring the data to the data center and analyze it there and store it there. No reason. Just want to give you yes and no. So this is the new architecture that we're moving to, and it's also changed the way that we design systems. Make it more interesting or maybe a little bit more complicated. Because if in the past, when you design a system, and you figure out how many flops you need, which determine how many CPUs you're going to buy, what's the bandwidth of the network or the I/O, and then how much data you want to store, that's going to give you the requirement for the different elements. Now where each element actually gives you compute, that changed the way that you architect the system. And this is new concept that we're going to see more and more, and we need to get used to. So the first elements that are happening is that, going back to the traditional way, is that you have the CPU. The CPU has running or managing all the network functions, and then you have the communication frameworks. For example, what DK described, and then you have the actually workloads. And everything runs on a CPU. The network is just an entity to move data, and the storage is just an entity to store it. What happened in the past so far is that the network functions were moved from the CPU to the network. All right, so you can do RDMA, for example, on InfiniBand or Ethernet or Cray and so forth. You can do other network functions on the network and not on the CPU, which reduce the overhead on the CPU side. But now what's also happening is that the communication framework is also moving to the network. And actually, more and more MPI, MPIGAS, UPC, you name it, but more functions of MPI is actually being run on the network and not on the CPU. So you can do collective operations, you can do tag matching operations, you can run rendezvous protocols, actually on the network and not on the CPU side. Now, as you look ahead, the goal of several organizations is actually to move the entire MPI stack to the network. So you want to get 100% of the MPI to run on the network itself and not run on the CPU at all. So the CPU will just run the workload. which means Dicky will have more interesting or further interesting things to work on and many more papers to write, because they're going to be a very interesting transition in the way that you implement and design the MPI elements. And then also you're going to move some of the workloads to the storage, because you can do also things there. You don't need to just do things on the compute side, on the CPU side. One more thing before I kind of complete it. One way to implement that architecture is moving cores and place them in different places. That's one way to do it. And you see, for example, network devices that now come with FPGAs or different cores. And Microsoft is now talking about they're using FPGAs on every network device because they need to run algorithms on the data itself and not just to wait for the data to go to the CPU. So this is one thing that we're going to see more and more. But just throwing cores on different places will not always make it. Because if I want to analyze data as a data move, and I'm just putting CPUs on switch devices and so forth, I actually create further limitations. The main element with moving things to other places is making sure that you don't stop data. So you want to be able to analyze data as it's stored or as it moves without stopping it and so forth. So we will see more interesting or compute capabilities implemented within ASICs and not rather with just putting more cores in different places. So that's kind of the first step we're heading. This is one of the elements that we'll see on the core systems. So Summit is being deployed. I'm sure that supercomputing will see at least part of it, probably in the top 500, and there are going to be multiple talks about architecture of Summit, which is a new architecture. But that's actually where things are moving towards. If we're looking from the MPI perspective, we're actually going to see MPI on the network in the future. So from the concept perspective, we're happy to work with multiple vendors and end users on that technology transition and learn more about what people are doing and also participate in that. We do plan to be able to run and collect more information about how things are going to run on Summit, which will be definitely interesting, and see how it's going to be used in other systems. Thank you very much.